Greetings, everyone. Welcome to this 11th session. And today we will be solving more assignment problems. And as you all know, that this course is about to end, and we will be having just one live session after this. So, today, let me start with the previously solved assignment, and we had reached up to question number 5. Now, today it says that we have to solve this question number 6. It says that we have to consider a MOS structure, that is metal oxide semiconductor structure with p-type semiconductor substrate, and it is doped with acceptor of the concentration 10 to the power of 16 per centimeter cube. And also we have been given the oxide thickness, and it is given to be equal to 50 nanometer. And we have been told that there are some charges that are present at the oxide interface. So these charges will definitely contribute to our uh, flat band voltages or the threshold voltages. So in here, it says that we have to compute that flat band voltage, because now this charge density will largely affect the threshold voltage, this oxide charge density. So we have also been told that this semiconductor metal work function is given to be equal to minus zero point 0.8 volts. So let me write it down like this. Let me start writing the solution for this. So the solution for this will simply be that if we have this flat band voltage in presence of, since we have this oxide surface charge, this flat band voltage, where this is the flat band voltage, this flat band voltage will simply be equal to phi ms minus wait a second, this will simply be equal to phi ms minus q equivalent divided by the oxide capacitance per unit area, since this surface charge density is also in per unit area. So this surface charge density is given to be equal to 16 nanocoulomb per centimeter square, as you can see from this. And we have been given this phi ms value. This phi ms is equal to minus zero point 0.8 volt. And this Q equivalent is simply equal to 16 nanocoulomb minus 9. Now this Cox is simply given by epsilon ox by Tox, where this Tox is the thickness of the oxide. Now we have been given this thickness to be equal to 50 nanometers. So let us substitute it over here. It will become minus zero point 0.8 minus 16 into 10 to the power of minus 19, 10 to the power of minus 19. This epsilon ox will simply be equal to 3.9 into 8.85 into 10 raised power minus 14. And this Tox will move up, and we are having it 50 nanometer. It means 50 into 10 raised power minus 9 meter, but we are dealing in centimeters, so the meter will be converted to the centimeter. So it will be 50 into 10 to the power of minus 7. So let us solve this on calculator to check this flat band voltage. So it's 16 multiplied by 15 divided by 3.9, 8.85. So this value, if I write it over here, this flat band voltage will simply be equal to minus zero point 0.8. Sorry, this will simply be equal to minus zero point 0.8, and this came out to be equal to 0.2317. 0.2317. Now, if I add these values, it should simply give me the flat band voltage. So it comes out to be equal to minus 1.03 volts approximately. So this is our flat band voltage that we were required to find in this problem. Now, this seventh problem, it says that we have to we have some MOSFET, and the MOSFET is having the N channel type, and this statement is there. It says that we have this N type, and is this N type is better than the P type in which of the following aspect. So we have been given four options, and we have been told to find the suitable option for this. Clearly, I have written the reason over here. It says that the current in the NMOS are there, since its current is carried by the electrons wholly, and in the PMOS the current is carried by the holes. The electrons in silicon, I have written it explicitly over here. Wait a second. Electrons in silicon have got higher mobility than holes. So NMOS is better than PMOS in terms of mobility. So we will go with option B. But let me remind you one thing. Basically, what we are saying over here is that these holes are heavier in case of silicon. But this might not be the case with every material that is present in the universe. For example, we will be having some material in which we will be having the EK relationship where the holes will be lighter. So in that case, the materials which will be forming the PMOS will be having better mobility, because in those materials the holes will have less effective mass. So it basically depends on the curvature. It depends on the EK diagram. So since we are talking about silicon in here, and silicon, as we know, it has less effective mass for the electrons as compared to the holes. So they will be having high mobility as compared to the holes. So the NMOS will be more suitable for faster operations as compared to the P channel uh, P channel devices for the silicon based devices. Let's move towards another problem. It has been shown that there is some MOSFET over here. We can see that. Let me use another color. That we have been given some MOSFET, and this MOSFET M1 is having the parameters like W by L is given to be equal to 2, and the operating voltage VDD is given to be equal to 2 volts. Now this K is also given to be equal to 100, where this K is the mu and Cox. And we have been given the threshold voltage, and this threshold voltage is given to be equal to 0.5 volts. We have been told that this transistor M1 over here, it switches from saturation saturation to linear region. So since it switches from saturation to linear region, so it will be good assumption to consider it in saturation region itself first. So since it depends whether a MOSFET is in saturation or whether it is in linear region, it depends on the voltages that are being applied to its drain to source and gate to source. And obviously, for a particular threshold voltage, I am saying for a particular threshold voltage, it will depend on the gate to source and drain to source voltages. Obviously, it will depend on the threshold voltage as well, but I am here talking about the particular threshold voltage. Like as in here, we are taking just one threshold voltage, that is zero point 0.5 volts. So it will depend on the biases that are present over this terminal and this terminal, since our source terminal is grounded. So we will simply try to evaluate this transistor in saturation region first. Let us write down the current equation in the saturation region for this MOSFET. So let us write this solution like this. So if I now take this M1 is in saturation. So the current expression for this MOSFET will simply be equal to ID is equal to 1 half mu n C ox, and this will be W by L VGS minus VTH whole square. So this is our current expression for the MOSFET. Now we have been given some parameter values that we need to put over here, like we have been given the value for this mu n C ox. Mu n C ox was given to be equal to 100 microampere per volt square. So I will take it to be equal to 100. This is microampere per volt square. 100 microampere per volt square, and this W by L is given to be equal to 2. So this is equal to 2. Now this VGS will simply be this voltage minus this voltage. This is the VGS. Now VGS is simply equal to, if I write it over here, VGS is equal to V in minus 0. So VGS is simply equal to V in, that is the input voltage that we are applying. So let me put it over here. This VGS is simply equal to V in minus the VTH. VTH is 0.5 volts. So this is our equation. So let us solve this. It will simply become 10 to the power of minus 4 V in minus 0.5 whole square. Now we have been told that this M1 MOSFET, it switches from saturation it switches from saturation to linear region. We know one thing for sure, that when we have this VDS to be equal to VGS minus VTH, we will be at the edge of this region when we will be just switching from the saturation region to the linear region, because we know when this voltage VDS is greater than VGS minus VTH, we say that the MOSFET is in saturation region. And when it is less than this particular voltage VGS minus VTH, we say that the MOSFET is in linear region. So if I now see what is this VDS, let us use some different color. This VDS, this is the VDS, and this VDS is simply equal to V out minus 0. So we have VDS to be equal to V out. Now let us put this VDS to be equal to V out, and let me use some other relation as well. This VDS is equal to V out. Let us keep it as it is, and this VGS is V in minus VTH. So I can just use some manipulations to incorporate this V out. This V out, if I simply say there is some current that is moving in this circuitry, this is some current I, and this same current is going into this MOSFET. I will be having this current I. This will simply be equal to, if I simply say this current IT will simply be equal to VDD minus V out by R. So it will simply be equal to VDD minus V out by R. Now let's add some slide. Now we have this relation, this VDD. So this V out will simply be equal to VDD minus I times this R. This but we know this V out is equal to VDS. We can simply say this VDD minus I times this resistance is equal to VDS. Now, if I use this value and put it, okay, and now if I use this value and put it over here, that since we know this VDS is equal to V in minus VTH, so let us say this VDS is equal to V in minus VTH. So it will become VDD minus IR is equal to V in minus VTH. So simple. Now from this we can put the value of this current, this I, this ID. This is same as this current I, this ID. This ID is same as this current I that is going into this circuitry. We will simply write it to be equal to VDD minus this ID. This ID is simply equal to 10 to the power minus 4 into this resistance, right? Let me write it down, V in minus 0.5 whole squared. This resistance is having the value of 10K. It is over here. It is having the value of 10K. So it is 10 into 10 to the power of 3, and this is equal to V in minus VTH. We have been given the value of this VDD. This VDD is equal to 2 volts. Okay. So this will become 2 minus this 10 to the power minus 4 will go with this 10 to the power plus 4, and we will be left with V in minus of 0.5 whole square, and this is V in minus 0.5. Now let us do simple manipulations. It will become V in minus zero point 0.5 whole square, and this will be V in minus zero point 0.5, and this will be minus 2. Now let me solve this quadratic equation. Let me write down it directly. It will become V in is equal to, sorry, let me write it down like this. V in minus zero point 0.5 is equal to minus 1 plus minus 4 times 8 plus 1 is 3. Its square root is 3 divided by 2. So let's add some slide. So it becomes this V in minus 1 plus 3. So I can't use minus 3 over here because we know we have to bias this MOSFET in saturation region first. So this if we are using negative bias, we will never be able to get this VGS equal greater than VTH. So that would mean we will be having the off state of that MOSFET in that particular voltage condition. But since we have to consider that we are switching from the saturation to the linear region, it becomes necessary for us to consider the positive magnitude of this voltage. So we will add minus 1 plus 3 divided by 2, it should become 1. So this will become V in minus zero point 0.5 to be equal to 1, or we have this V in simply to be equal to 1.5 volts. So we have got this voltage at which we will be switching from this saturation region to the linear region. Now let's move towards another assignment. This assignment, yes, 8th question has been done. Okay, let me move towards another assignment. It says that we have to now solve this assignment number 10. It says that we are operating the MOSFET in some threshold sub-threshold condition, and this sub-threshold current has been, as we know, it will be having this exponential dependence, and this exponential dependence is given by the term over here. This term incorporates this factor of the interface states, and it is given to be equal to 2.1 volt. And this MOSFET is in saturation, this sorry subthreshold region for this bias of 0 to 1 volts. The gate to source voltage has to be between 0 to 1 volt, and this threshold voltage, this thermal voltage has been given to us. It is 25.9 millivolts, and we have been told to assume that there are 10 to the power 6 identical transistors on the chip, and they are all biased at the same VGS and at the same VDD. So the operating voltage is 5 volts. Now we have been told to calculate the ratio of this subthreshold current that will be present in this MOSFET at two bias voltages. One is zero point 0.7 volts and the other is 0.5 volts. So it is simple manipulation. We have to just use this current equation. This is ID. Let me write down this current equation first. It is ID is equal to 10 to the power minus 15, 10 to the power of minus 15 exponential of VGS divided by 2.1 into VT. Let me check. Yes, it is 10 to the power of minus 15 exponential of VGS divided by 2.1 VT. Now we have two bias voltages when one is zero point 0.7 volt and other is zero point 0.5 volts. So we have VGS1 equal to zero point 0.7 volts and we have VGS2 to be equal to zero point 0.5 volts. Let us find the current ID1. It will simply be equal to 10 to the power of minus 15 exponential of this VGS1 is simply zero point 0.7 divided by 2.1 into 25.9 into 10 raised to the power minus 3. And ID2 is simply equal to 10 to the power of minus 15 exponential of zero point 0.5 divided by 2.1 into 25.9 into 10 to the power of minus 3. Now we have been told to find the ratio of the subthreshold current in the MOSFET device at the two voltages, that is VGS equal to zero point 0.7 and zero point 0.5. So let us name this equation 1 and this as 2, dividing equation 1 by equation 2. So it will simply be ID1 by ID2. This, let me cancel these three factors. This and this will go, and we will simply be left with exponential of zero point 0.7 minus zero point 0.5 divided by 2.1 into 25.9 into 10 to the power of minus 3. So it will simply be equal to exponential of zero point 0.2 divided by 2.1 into 25.9 into 10 to the power of minus 3. So let's solve this expression. Wait a second. Let me solve this expression. 0.2 divided by 2.1 is exponential of 3.67. Exponential of 3.67. So it comes out to be equal to, let me write down this on another slide. So this comes out to be equal to ID1 by ID2. It approximately comes out to be equal to 39.6. So it is option C, which is matching. It is approximately equal to 39.5. So we have been able to solve this question by just equating these current values. Now it says that we have to uh, calculate the total current that must be supplied to the chip at this VGS equal to zero point 0.7. So the solution to this will simply be equal to, we have to find the current, total current at some gate voltage, which is zero point 0.7 volts. So let us write down the current expression again. It is equal to 10 to the power of minus 15 exponential of VGS divided by 2.1 into VT. This was our current expression. So this will simply be equal to 10 to the power of minus 15 exponential of VGS will be simply equal to zero point 0.7 by 2.1 into 25.9 into 10 to the power of minus 3. So this is the current of the one transistor on a chip. Now, the total current on this total current, we need total current, and but we have been given that there are 10 to the power of 6 identical transistors that are present on a chip, and they are all biased on with this same VGS. So all those transistors are now biased at zero point 0.7 volt. So it means we have this transistor biased at zero point 0.7 volts. So let me write down this N to be equal to number of transistors on a chip. So this total current, let's add some slide. This total current will simply be equal to this I total will simply equal to N times this ID. So it will simply be equal to 10 to the power of 6 is the number of transistors. This ID is 10 to the power of minus 15. And this exponential of, let us calculate this exponential first, 0.7 divided by 2.1. So it comes out to be equal to 3.88486 into 10 to the power 5. So it comes out to be equal to 3.88486 into 10 to the power of 5. So let's take it up to this decimal only, 3.88. So it will simply be equal to 0. If I take this 10 to the power minus 5, this will be 10 to the power plus 5, this will be 10 to the power minus 10, will 10 to the power minus 4. So this will be 3.88 into 10 to the power minus 4 amperes. So if I convert this into milliampere, this will be 0.388 milliampere. Now let us check down the options if it's matching with any one. Yes, it is matching with the first option. So we have got the total current that needs to be supplied for this chip at some gate voltage of 0.7 volt. Now there is another problem related to this same question. It says that with reference to the details that were given in question 1, we have to calculate the power dissipation. So in this problem, we have to calculate the power dissipation. We know this power this power dissipated, if I denoted by P this is the power dissipated. We know this power dissipated will be equal to the applied operating voltage, that is VDD, into the total current. Now this total current needs to be calculated on a particular bias, and this time the bias is zero point 0.9 volts. Now we have to calculate this total current first for the uh, this bias. Let us write down this ID is equal to 10 to the power of minus 15 exponential of VGS by 2.1 VT. So it will simply mean 10 to the power of minus 15 into exponential of zero point 0.9 by 2.1 into 25.9 into 10 to the power of minus 3. So I have calculated this previously. So it should come out to be equal to 1 10 to the power of minus 15 into 15 into this number should be equal to simply 15.35 into 10 to the power of 6. So this is in amperes. Now I need to find the total current. The total current will simply be equal to this I total will simply be equal to N, where N is number of transistors on the chip, into this ID. This ID is 10 to the power of minus 15 is 10 to the power of minus 9 into 15.35. 3358. Sorry, it is 10 to the power of minus 9. Okay, yes. Now, this has to be multiplied by this number, where this number is n is 10 to the power of 6. Let us multiply it beforehand so that we don't get confused where this number came from. So it will simply be equal to 15.358 into 10 to the power of minus 3 amperes, or it is equal to 15.358 milliamperes. But we require to find the power dissipated over here. This power dissipated is equal to VDD into I total. This power dissipated is equal to VDD. We know from question 1 is 5 volts. So it is 5 into 15.358 into 10 to the power of minus 3. So let me multiply this number, okay, into 5. So it will come out to be approximately equal to 77 into 10 to the power minus 3 watts. Let us check the options. The answer is in milliwatts, so it will simply be 77 milliwatts. So let's check the option. Option D is matching, so we will select the option D. Now, uh, we have been given a MOS device with some parameters. Wait a second, with following parameters. Uh, the accepted doping is given to be equal to 10 to the power of 16 per centimeter cube, and the oxide thickness is given to be equal to 20 nanometer. We have been told to find the body effect coefficient. Now, this is simple. We just need to find this expression, this gamma. This gamma is the body coefficient. As we know, it is equal to 2 times epsilon s and a over c. Can anyone? Oh, sorry, I have put the units. Should have put. Can anyone tell me what are units of this gamma?
It's unitless.
Let us see. Okay, fine. So, uh, let me calculate this value. Since we have to be a bit careful about the units, we should always go for dimensionality check whenever we are doing multiplications or addition of two quantities. Since we know this gamma, if I check here units, which is not necessary over here, but if we know this gamma is having some expression which is like this, gamma times, if we have to just include this VSB effect, this will be VSB plus some voltage which is the surface potential, which is the pinning surface potential, for example, pi fp. If this is the multiplication factor for something, this is having the units of volt hour, this quantity. Now, if we have to add it with some voltage VTHO, this is the general voltage without the body effect. This voltage is having this VTHO is having the units of voltage itself. Now this quantity over here is having the units of root of volt. So we simply have to check the units of this by saying that this will have the units of root of volt, because we can add the quantities having the same units only. We have to add volt with volt. So it is just even not going into the dimensionality check for this thing. We didn't went for the units of the like Na, epsilon s, q, cox. We didn't went for their units. We just saw by this simple expression, if we have to add two voltages and we have another voltage which is in the multiplication factor, this is having the units of voltage, and since it has square root over itself, so it will mean that it is having the units of root of volt. And we have some quantity that is multiplying this factor is multiplying this quantity. It would mean that I have to multiply by this quantity so that this quantity overall is having the units of volt. So this is just a simple check to say that this gamma will be having the units of root of volt. So if we now say that this Na, uh, before that, oh, let's calculate this gamma directly. This is 2 times 1.6 into 10 to the power of minus 19, and this epsilon s is for silicon. We are considering the silicon case only. This 11.7 into 8.85 into 10 to the power of minus 14. Wait a second. 10 to the power of minus 14. This will be under the square root into 10 to the power of 16 divided by epsilon ox. This epsilon ox by T ox. This is 3.9 into 8.85 into 10 to the power of minus 14. And we have to divide this thing by T ox is 20 nanometer. It is 20 into 10 to the power minus 9, but we are dealing in centimeters. So I have to take it, I have to convert this meter into centimeter. So it becomes 10 to the power of minus 7 centimeter. Now let us calculate this quantity on our calculators. So it would mean 2 into 1.6 into 11.7 to multiply. So it would simply be, this will be equal to root of 351.344 into 10 to the power of minus 70 divided by, this will simply be divided by 3.9, 8.85, 1.725, 1.725 into 10 to the power of minus 7. Okay. So let me divide these quantities again. I just wrote it for my calculation purposes. 313.1. It is 5.75 into 10 to the power of minus 8. Minus 8 divided by 1.725. It will be 0.335. 0.335. So 0.33. Okay. It will be 0.33. This. Wait a second, let us add some slide. It will be equal to 0.333 volt half. So the option, okay, this option B is matching our calculation. So we got this option correct. Now we have been told to find the uh, for this MOS device. In same question, we have been told to calculate the threshold voltage change for some VSP of 1 volt. That's why we have found this gamma previously, so that we can use it in this question. Now it says that we have to calculate the threshold voltage change. We know if there is no VSB and this VSB, this delta VT will simply be given by this gamma factor will simply be having this 2 phi fp, where this is the pinned surface potential. We have assumed that the surface potential is pinned at 2 phi fp for this p-type substrate, plus VSB minus times this 2 phi fp. Now in here we need to find this phi fp first, because we have been given the concentration. Yes, we have been given the concentration 10 to the power of 16. So this phi f, not phi of b, phi of p, this phi fp is simply equal to Vt ln of Na by Ni, that we all know. And this Vt is equal to 25.9 into 10 to the power of minus 3 volts. And this is ln of Na is 10 to the power of 16. Yes, it is 10 to the power of 16. And this Ni is the intrinsic carrier concentration, and it is given to be equal to 1.5 into 10 to the power 10 for the silicon. It is 1.5 into 10 to the power of 10. Now let us solve this. Simply ln of 10 to the power of 6, 2, 3, 5. It is 13.4 into 25.9 into 10 to the power minus 3. So it will come out to be equal to 0.35. So this phi fp will come out to be equal to 0.35, and it will be having the units of volt. Because let us check another thing over here. This is having the units of volt, and in exponential or in ln, we always have the unitless quantities. We should have the unitless quantity. This number over here, this in Na acceptor concentration, is having the units of centimeter cube per centimeter cube. This is also having the units of per centimeter cube. So this makes our life easy. Clearly, this centimeter cube and this centimeter cube will go. We will be having this quantity as unitless. And now this Vt is having the units of volt, and it will simply mean this phi fp is having the unit of volts. Now we have seen this phi fp, we have seen this gamma value. We can substitute these values over here and calculate this delta Vt, that is the threshold voltage shift. It will simply be equal to, gamma came out to be equal to 0.33 root of volt. So it is 0.333 root of volt. 25 Fp is simply equal to 2 times 0.35 plus VSB is equal to 1, and this 25Fp is simply equal to root of 0.35 square. Now let us again do the calculations. This is 0.35 into 2 plus 1 root of 1.7. Root of 1.7 is 1.303. It will simply be equal to, let's add some slides, 0.333. It is simply equal to 1.3038. Okay, minus of root of zero point 0.7 minus 0.8366 minus of 1.3038 into 0.333. It is 0.155. It is 0.1555. So this threshold voltage shift is equal to 0.155. Let's check the options. Okay, it is 0.16 and we can choose this because it is 0.1555 and we know that we can round off to this value. So we will choose this value and select this number as 0.16 volts. Now let's move to this question 6. Okay, this question 6 says that we have to consider an N-channel MOSFET with the channel width of 30 micrometer and the channel length of 1 micrometer. And the oxide capacitance is given to be equal to uh, 69 nanofarad per centimeter square, and the drain current is drain current in the saturation for this small VDS. It means that we are operating in linear region because this drain current is very less and it is given to be equal to 0.07 volts, and this ID, this drain current value is going to be equal to 25 microampere at VGS equal to 1.5 volts, and this ID at VGS equal to 2.5 volts is going to be equal to 65 microampere. So we have been told to find the mobility in this case. And we have two unknown quantities over here. One is the threshold voltage and the other is the mobility. I think it will be a bit time consuming question. So let's do it in next class, and let's move towards these questions which are present in our slides, which are a bit theoretical, I think. Yes, let's see this question first. It says that which of the following statements are true? So this it says that interface states affect the subthreshold swing of a MOSFET due to the presence of additional capacitances. And this statement is obviously true because we know if we are having the additional capacitances, it is going to affect the charge because there will be some charge that will be associated with it, and it will affect our uh, what we can say the threshold voltage, the IV characteristics, because it is going to affect our uh, the when what does the charge do? This charge will simply affect when we are solving for the Poisson equation. When we solve for the Poisson equation, it incorporates charge. So if we are doing any what we can say tinkering with the charge, we are changing the charge a bit, the Poisson equation will solve differently. So this charge is going to affect the subthreshold swing, obviously. So this interface states will be having charge, and these will give arise to some capacitances, and thus these capacitances will affect our MOSFET operation. So this statement one is true. Let us use a black color to write true for this. Now the another statement is that the CV characteristics of a MOS system shift left or right based on the presence of trap oxide charges in the oxide. We know that if we are having, for example, P substrate, and we are just having positive oxide charges, these positive oxide charges will attract more electrons that then this would mean we will be requiring less amount of gate voltage as compared to the previously uh, required gate voltage that was present when we were having no oxide charge. When there was no oxide charge, for example, we needed 1 volt, but now we are having some positive oxide charge that has already caused a bit of inversion in the channel. So it would mean we will be requiring less gate voltage. Let's say we will be requiring 0.8 volt now. So it would mean that the CV curve will shift now towards the left. Similarly, it can shift towards the right as well. So it simply means that this is capacitance curve, this CV curve, we can change it by the presence of the traps that are present in the oxides. So these oxide charges will shift this from left to right, and accordingly it will be moving. So this statement is true. Now there is another statement. It says that this presence of trap charges has no effect on the CV characteristics of a MOSFET. We saw this just now, that this is false because these trap charges are going to affect the, obviously they are going to affect the our capacitances because they will be shifting this CV curve. So this will be false statement. Now, the fourth term says that these charges present at the oxide and semiconductor interface has strong effects on the threshold voltage value. We can just by saying that if in the previous question when we solve this, like, okay, did I solve for that? Yes. Uh, like that, we had some oxide surface charge density. It affected our flat band voltage. Had there been no equivalent charge oxide at the oxide, we would have got this flat band voltage just equal to the phi ns. But since there was this oxide this charge on the oxide, it meant that there will be the shifting of this threshold voltage because we, we might be requiring less or more threshold voltage. It will just depend upon the charge carrier density, whether it was positive or whether it was negative. So I think it is, let's come to close for today. And if we have no questions, we can end today's session. So if we have questions, we can take those.
So question number three.
Question number three. One second. One second. One second. Okay, this one.
Yes, sir. No, no,
Okay,
no. Question of four.
okay. Question number four. Okay.
No, no, no. So what is the reference question? Question number. The next slide. Can you take, sir?
This slide,
Yes, yes. Assignment 10, question number 3.
assignment question number three. Yeah, yes, here it is.
Yes, yes.
Okay. Uh, uh, I have to repeat this. Okay, I can repeat this. So we know that this, if we have to calculate the power dissipation in some circuit, it will just be the amount of voltage that we're applying to it and the total current that is present. So this we know that this is the multiplication of this V and I. So we are giving some voltage to the circuit. For example, there is circuit having 10 transistors and we are applying some operating voltage of, like here we are operating 2 volts. And in here it has been told that each transistor is having same VGS. So it would mean that we need to find the current that is present in the one transistor at a particular bias. And we were told that the current is given simply by this 10 to the power of minus 15. This was in sub-threshold region. 10 to the power of minus 15 exponential of VGS by 2.1 VGS. So we just put the VGS value in this expression to get the current per transistor. We got this current value for current per transistor. This was the value. It came out to be equal to 15.3 into 10 raised to power minus 9 ampere. So we needed the total current because there might be many transistors present in the circuitry, and like in here we are having 10 to the power of 6 transistors that are present in the circuitry. So we just multiply by that number of transistors because we know that they are identical. There will be this much amount of current in the total circuitry that is present now. So
So 10 to the power minus 9. This value came from where? Or what you...
okay, this value came from here. 10 to the power of minus 15 into 10 to the power of 9. How much it is?
Okay, okay, sir. Okay.
Okay, huh? Okay, fine. It's 10 to the power of minus 9. So we multiplied it and we got this total current to be equal to 15.358 milliamperes. So this was the current that was present in these number of transistors, that is 10 to the power 6 transistors. Now we simply multiplied by this VDD, that was the operating voltage, and that was given in question 1. This is the VDD value, this operating voltage. So we simply multiplied by this current value by the VDD value, and we got the power that will be dissipated in the circuit. Okay.
Yes, sir. Thank you, sir.
Okay, okay, thank you. Thank you then. We can end today's session. Thank you for joining.
Thank you, sir.
Thank you, sir.
Huh? Okay, okay. Thank you, thank you.